All right, graphing the other trig functions. So we're doing tangent and cotangent and then secant and cosecant. So tangent and cotangent are going to be very, very similar to each other. They're also done a similar process to sine and cosine, but be careful not to get things mixed up. So review your formulas here for tangent. Here's our first example. So graph f of x equals 3 times tangent of 2 times the quantity x minus pi force plus 1. All right, it's in the right format, so we can go straight into figuring stuff out. So first thing we need to do is get our period. I'm not zoomed in enough. All right, period. Formula for the period for tangent, be careful, pi over the absolute value of b. So pi over b, which is, that's crooked, 2. Pi halves is our period. Then we need to get our alignment of our tangent uses inflection points and asymptotes. So our inflection points are going to align along the horizontal line y equals 1, our D. So we can still call it the axis, I guess. So y equals 1, so that's where we're going to align all of our inflection values when we get to them. We need our phase shift. So this was shifted right pi force. So that's going to be our starting critical point, pi force. And then our count by, 1/2 p. So half of pi half. So pi 4. All right. The amplitude, that vertical stretch compression factor is not really going to affect us drawing this graph, so we're not even going to bring it into anything. All right, tangent starts inflection value. So tangent is theta. And then it just continues on down the road. So inflection value is going to be that pi force, where our phase shift was. And then we add our count bys to get the rest. So I'm going to add pi force. So that's going to be 2 pi force, 3 pi force, 4 pi force, and so on, however many you want to put. Then I like to go left, so minus pi force, 0, minus another pi force, negative pi force. I'll always draw one negative critical value. All right, a graph. Get my tick marks on. I should have done this before I started the video. Go away. Oh, those are different colors. Hang on, that's going to bother me. Style, blue, done. Okay. There's our blue. All right. Whoa. Too many buttons. Let me copy this. Copy. And I'm just going to paste it down here. That way I can drag it down for the next graph. All right. So since we do hit 0, I'm going to go ahead and get my y-axis in. We're going along y equals 1. Get my critical values, negative pi 4, pi 4, pi half, 3 pi 4, 4 pi 4. I got one more, so 5 pi 4. All right, asymptotes versus inflection values. Let me get my asymptote ready to go. All right, tangent starts inflection point. So our first inflection point is along pi force, aligning along the horizontal y equals 1. Next, critical value is an asymptote. Then we just continue this process. Inflection, asymptote, inflection, and then mirror it back the other way. Next, I need an asymptote on 0, and then I need an inflection. All right, tangent increases from left to right, so when we draw our little wiggles, make sure they are increasing, and then that concavity changes at that point. So I draw them better this direction. Still not very pretty, but we get the idea. So there's our graph. I'm gonna move this on down here. I'll come back up in a second. Right now I'm just trying to get it. Why is it so tiny? Or blow it up. Copy. I'm gonna go ahead and get them down here for the rest of them. Paste. Paste. Okay. All right, next thing we're looking at is graphing cotangent. So cotangent is very, very similar to tangent, with the exception of cotangent starts with an asymptote, so it's backwards, and it decreases from left to right rather than increasing like tangent does. All right, it's not in the right format this time, so we got to do some manipulating. Separate the -2 from the x, which means that pi force has to be multiplied by its reciprocal negative. Flip it, 1/2. No addition, subtraction at the back. All right, so we've got negative cotangent -2 times the quantity x minus pi 8. Close, close. All right, cotangent, negative inside. Cotangent, remember from our identities, is an odd function, so a negative inside bumps to the outside, but because there's already a negative on the outside, a double negative is going to give us a positive a. So we will be graphing positive cotangent. All right, ready to go. All right, period. Pi over b, which is going to be pi halves. Axis, y equals 0, since there was no shift up or down. So they're going to align on the x-axis. We need our phase shift. That starting critical value, which is going to be right 8, so it's at x equals pi 8. And then we need our count by, 1/2 p. So half of pi halves, pi 4. All right, graphing cotangent. Cotangent starts asymptote. First asymptote at that critical value, pi 8. And then we are adding pi 4, which would be 2 pi 8. So we're adding 2. So 3 pi 8. 5 pi 8. Write as many as you need to get the pattern. 7 pi 8, so forth and so on. That's plenty for me. I'm going to go to the left to get one negative. So I subtract pi 4, so that's going to be negative pi 8. So notice 0 is not listed as one of our critical values here. All right, graph. Made the graph a little bit bigger. Scoochie. All right, let me get them all labeled first. So negative pi 8, positive pi over 8, 3, adding 2. Oh, that's crooked. Seven, 9, and 11. I'm just going to go till I run out rather than shorten the graph. All right, y-axis is going to go right in the middle here. So I got that drawn in. I don't need any values labeled on the y-axis since there was no vertical shift, so we're ready to get going on the graph. Okay, first value is an asymptote, and that asymptote goes along x equals pi 8. So and then every other critical value gets an asymptote. So if you want to draw all your asymptotes first, you can. Just make sure you're skipping critical values. So 1, 2. And then we got another one here. And then if we go back the other way, we're not going to see one because I've got my inflection, asymptote, inflection, asymptote, inflection. Go left, inflection, asymptote, inflection. Positive cotangent decreases from left to right. So we're going to wiggle down. wiggle, down, and wiggle, down. All right, going into secant and cosecant. So graphing secant and cosecant, we like these is because we're going to use the same idea that we did with graphing sine and cosine, with the exception of all of our A's now represent the location of asymptotes rather than axis points. And we're going to turn our highs up and we're going to turn our lows down. Okay, so we'll go over a more visual of that when we get to drawing this first graph. So first we'll run into secant. We'll go over properties. There's your properties for secant. Secant's reciprocal is cosine. So we're going to use the strategy for cosine for getting the secant function graphed. All right, first we want to get it in the right format since it's not. So we've got f of x equals 2 secant, separating that pi half from the x, which means the pi is being multiplied by the reciprocal 2 over pi. Clean up the inside. So f of x is 2 secant of the quantity pi over 2 times x plus 2, close, close, plus 1. All right, period. Like I said, we're using cosine, 2 pi over b. So 2 pi divided by pi half. Keep it, change it, flip it. So that's 2 pi times 2 over pi. Pi's drop and we get 4. The axis here doesn't really help you unless you like it written down to find your highs and lows. Again, that's up to you. Axis, we're not going to draw it on the graph at all, is y equals 1. And our amplitude, which is going to be the distance from that axis to where we're going to turn our highs out and turn our lows out, is going to be 2. Phase shift. Starting critical point is x equals plus, so we're going left 2 units, so -2. And our count by 1/4 of p, just like sine cosine, so 1/4 of 4, 1. All right, graph. We are graphing. Secant, secant's reciprocal is cosine, so that would be chala. Starting critical is -2. Then we add our count by to get the rest. So we're going to add 1, add 1, add 1, add 1. All right, we do hit 0, so that means I can go ahead and insert my y-axis. I get 2 negatives, and then my y-axis. I get those labeled. Nope, that color. -2, -1, 0, 1, 2, 3, 4. All right, for our y-axis, so we know the axis is at 1. We're going to go up 2 to get our high. So our high is going to be 3. And then we're going to go down 2 to get our low. So our low is going to be -1. All right, graph. So we have a high at -2. Highs and lows, dots. A's, asymptotes. We have an asymptote at -1. We have a low at 0. We have an asymptote at 1. High, 2. Asymptote, 3. Low, 4. So I'm going to sketch the graph of sine in real quick just so you can see it. Let me change colors. Well, no, I'll just dash it myself. Okay, so here's the graph of cosine. So here's our cosine graph. So you can see how it does run the insides of this. So when I say turn the highs out and the lows out, it means to the outside from the axis. So where that high is at -2, we are going to turn it out, bounded by those asymptotes. For -1, we're going to turn it out, bounded by those asymptotes. That one's kind of terrible. Turn out this high, and then turn out the low. So everything turns outside rather than inside, kind of in a U, similar, sort of looking parabola there. I just drew them really, really bad. All right. Properties of cosecant. So cosecant's reciprocal is sine, so we're going to use all the characteristics for sine that we used earlier. All right, first things first. Nothing to separate since there is no phase shift. However, we don't like negatives inside. Cosecant's reciprocal is sine. Cosecant is an odd function. So a negative inside becomes a negative outside. So that's the first thing we need to take care of. So we're worried about f of x equals -3 cosecant of 2x minus 1. All right, period. 2 pi over b. So 2 pi over 2 pi. Axis, if you like, along -1, but kind of pointless. Amplitude, 3. Phase shift, none. So I'm just going to put x equals 0 so that I know what that starting point is. And then our count by, 1/4 of p. And p was pi, so 1/4 of pi, pi over 4. All right, cosecant. So we're looking at sine. Sine is Sahala. However, make sure you remember this was negative sine, so that's not the one we want to look at. We want to swap our highs and lows. So we're going with Salaha. All right, starting at 0. Adding pi 4, so 1 pi 4, 2 pi 4, 3 pi 4, 4 pi 4. I'm going to go left because I always will show you a negative pi 4. All right, since we do hit 0, I can draw my y-axis in. Get my points labeled. We got 2 over 4. 3 over 4, 4 over 4, 5 over 4. All right, let's see, highs, lows. Our axis is at -1. We are going up 3, which is going to put us at 2. We go down 3, that's going to put us at -4. All right, starting at 0, 0 is an asymptote. Then we move to pi force. We are on a low. Come on, pin. Another asymptote. Then we move to a high. Another asymptote. And then to a low. Mirror it back to the left. We have an asymptote at 0. The critical point before that asymptote was a low. So this critical point is going to be a high. So you should still see that alternating zigzag. So I'll sketch your sine graph in here as well. So here's your little zigzag. And then we just turn out. So I'm going to turn the highs out towards infinity and the lows out towards negative infinity. Turn them out, turn them out, turn them out. So there's our cosecant graph. All right, 5, now we're going to go reverse it, write equations. So you could be given a graph. This one you're just given general information. So cosecant function with a period of 3 pi, a VA at x equals 1, and range below -2 including and above 2 also including. All right, so I'm going to go ahead and get my cosecant. Did it say cosecant? Yes, cosecant. So I'm just going to leave room for A, B, C, and D. All right, period, that's what I go to first. Period is 3 pi. Just like with sine and cosine, we're using the same information. If the period's 3 pi, we know the relationship is 2 pi divided by the one you know gives you the one you're missing. So 2 pi divided by p gives us b. So if we take 2 pi and divide it by 3 pi, we get 2/3. So the period is, or b is 2/3. So I can go ahead and fill that in. All right. Phase shift and amplitude, we're going to find those using the range. So for our range, we are going, the range like this is telling us that lower interval tells us that bottom turned out piece is starting at -2. The other one, the top piece turning up, is telling us that it is starting at +2. So our D value, our axis, is going to run right in between them. Oh, those are dashes. That's why that looks so weird. Let's get off the dashes. So right in between them is going to be our axis. So right in between there, that's going to be at 0. So D is 0 since they're evenly split. The amplitude is the distance apart from the axis to each of those, which is going to be 2. So our amplitude is 2. So we'll go fill those in. So the amplitude is 2. D is 0. There's no reason to put a +0 at the back. So next thing is our phase shift. We have a VA at x equals 1. So this is the graph of cosecant. Cosecant's reciprocal is sine. So we're going to use Sahala. All right, so Sahala, sine, and cosecant. Cosecant starts on an asymptote. We are given the location of an asymptote. So I don't need to worry about moving over any other critical values. I just need to start at 1, which means I'm going right 1 unit. So there's our function. And I would like to make the colors match. There we go. So there's our function. All right, B, graph of cotangent with a period of pi4 and VA at x equals pi8. So just leave some room for everything. All right, so this is pretty generalized. So the period being pi4, so it's the first thing I want to worry about. So period is pi/4. Relationship with tangent and cotangent, B and P have the same relationship, but it's pi/P, not 2 pi. Tangent, cotangent is pi. The other 4 use 2 pi. So that's going to be pi/pi4. We do keep change flip, pi times 4/pi. We get 4 for B. So I can go fill B in. All right, VA is the only other piece of information we're given. So we are graphing cotangent. Cotangent starts with an asymptote. So we're where we need to be. It's at pi8. So I need to shift over to pi8, which would be right. So minus pi8. The value of A, I could technically stick any value of A I wanted in there, and it's going to fit these two requirements. So there's no reason to mess with it. Let's just leave it at 1. And the value of D, we're not given the location of those inflection points, so they're not being restricted. So again, let's just keep it simple, and we're just going to leave D at 0 as well. If it said inflection point along y equals 7, we would then need to figure out the D value. But in this case, this is all we're concerned about.